In this problem, we are given the direct current circuit shown here. In order to find the magnitude of the conventional current in the 2-ohm resistor and the unknown battery voltage, we will use Kirchhoff's laws. We will also follow the strategy given in the text to apply these laws correctly. We begin by examining the number of loops in the circuit. There are 3 distinct loops. One loop is the bottom loop of the circuit consisting of the 6-ohm resistor, the 24-volt battery, the 2-ohm resistor, and the battery of unknown voltage. Another loop is the top loop consisting of the 6-ohm, 4-ohm, and 8-ohm resistors and the 24-volt battery. The third loop is the outer edge of the circuit consisting of the 4-ohm, 8-ohm, 2-ohm resistors, and the battery of unknown voltage. Only 2 of the loops can be used for this problem. Using the third loop would just give us an equation that would be the sum of the first 2 and therefore not an independent equation. We will get our third equation by using the junction rule. We will use the top loop, the bottom loop, and the junction rule to solve this problem. Let us begin with step 1 of the problem-solving strategy, drawing the directions of the currents in the top and bottom loops. Remember, our choice is just a guess. If we pick the wrong direction, we will end up with negative currents for the answers. We will start by drawing the current through the 6-ohm resistor as moving to the right. We will also place plus and minus signs on the ends of the resistor to show the higher electrical potential and lower electrical potential ends. These signs must be consistent with our choice of direction of the current, which flows from higher electrical potential to lower electrical potential. In the top loop, the current is shown to move from left to right in the upper part of the loop. We will place plus and minus signs on the 4 and 8-ohm resistors to indicate the high and low electrical potential ends of the resistors. Again, these signs must be consistent with the direction of current, which we assumed in that part of the loop. Now we will choose the direction of the current in the bottom part of the bottom loop to go from right to left. The plus and minus signs for the high and low electrical potential ends for the 2-ohm resistor will be drawn in as before to be consistent with the direction of the current in that branch. Let's label the currents in each branch and the resistors to help us with the equations in the next step. We will call I sub 1 the current through the 2-ohm resistor, I sub 2 in the current in the 6-ohm resistor, and I sub 3 the current through the 4-ohm and 8-ohm resistors. Let's also call the 2-ohm resistor R sub 1, the 6-ohm resistor R sub 2, the 4-ohm resistor R sub 3, and the 8-ohm resistor R sub 4. We will now apply the loop rule to the top loop to generate the first equation. We will start in the lower left-hand corner of the loop and follow the direction of the current, setting all electric potential drops equal to all electric potential gains. Using Ohm's law for the potential drop across a resistor gives us the following equation. We will now apply the loop rule to bottom loop to generate the second equation. We will start in the lower left-hand corner and follow the direction of the current, setting the potential drops equal to the potential gains. Using Ohm's law for the potential drop across a resistor again gives us the following equation. We will now apply the junction rule to the junction on the left side of the circuit, setting the currents leaving the junction equal to the currents entering the junction gives us a third equation. Examining these equations and remembering that I sub 3 is given, we see that equation 1 will give us I sub 2 immediately. Solving this equation for I sub 2 and substituting in the known values gives us the positive answer tells us that the direction for I sub 2 in the figure is correct. Using I sub 2 in equation 3 will give us I sub 1. Solving equation 3 for I sub 1 and substituting in the known values gives us our final unknown. Now we have enough information to find the unknown voltage using equation 2. Solving equation 2 for this unknown voltage and substituting in the known values gives us our final unknown, the voltage of the unknown battery.